Hello, Chemistry 12. This is Mr. Chan here. And today is the second lesson on equilibrium. And the one I want to focus on today is when I gave you the notes last day. Remember in the second bullet, it says here, if conditions change, the equilibrium rearranges itself or shifts until a new equilibrium is established. Now, what I want to do is I want to focus on that specifically for today's lesson, the second bullet. And when we talk about this equilibrium rearranging itself, what we're focusing on is something called Le Chatelier's principle. Okay, so what is Le Chatelier's principle? Now, for Le Chatelier's principle, it basically says this, that when there is a stress is a change in concentration, temperature, volume, or pressure. When that is placed on an equilibrium system, what happens is the equilibrium will shift or offset or counteract the applied stress, resulting in a new equilibrium. Now, so in chemistry, when we use the term stress, what we're talking about any change in the conditions. And when we talk about shift, what a shift is the rate that is initially faster. Now, when we talk about the rate initially faster, it goes back to our notes here. Remembering when, if I can just do this here, remembering in this particular case that the reactants and the products, one is being used up and the other is being produced. And so what happens is there's a forward and reverse rate that's constantly changing. And when equilibrium is reached, what you have is you have equal rates. Now, we talked about this last day, and hopefully you were able to watch the videos that were in the description box below in last day's lesson to illustrate the idea of equal rates using water being transferred from one beaker or one container to another. Now, when we talk about shift or stress, this can apply to us in real life as well. For you folks, sometimes things change. You either move schools or you take on a heavier course load or you change your classes. What happens is that is considered a stress because your conditions have changed. But what happens is how you adjust to it. This is what we call our shift. Now, so what I want to do is I want to talk about some general stresses. So what is one of the general stresses that we deal with is a change in concentration. Okay, so we have a change in concentration. What will happen is when there's a change in concentration, the equilibrium will shift towards the side with lower concentration. Now, what happens is when we talk about concentration, this mainly applies to solutions and gases, not pure solids or liquids. Now, why not pure solids or liquids is because of the fact that pure solids and liquids have a constant concentration. Okay, that is a key thing, is that pure solids or liquids have a constant concentration. So even though you might say, well, could we add more solid? If it's a pure solid, what happens is the amount might have increased, but the concentration or the density of the solid hasn't. Okay, now let me give you an example here. So let's say if we have our reactant is in equilibrium with product. Now, what I've done is I've just made a general reactant and product. Okay, it could be 20 reactants and 10 products or one reactant and two products. But what I've just done is made it a general equation of reactants going to products. And so what I have here is I have three particular categories. So I have the stress, I have the shift, and I have the result. Now, let's say for the shift, let's say I increase my concentration of product. Now, that is my stress. Okay, I've changed something. I've increased my product. What will be the shift? Now, let me just move this down here a bit. Okay, what is the shift? What will happen is we would say it would be to the reactant or to the left or the reverse rate is favored. Now, if you were in my class for this lesson, what I would have done is taken the water demo, and what I would have done is I would have shown you uh, visually what happens when you increase the concentration. I will see if I can find a video on YouTube, and I'll put the video in the description box below. But if not, what you can do is come and see me, and I can demo this idea of increasing the products and the shift to the reactants to the left or reverse rate favored. Okay, but what I'm going to do is I'm going to explain why. So in this particular case, when it is at equilibrium, the rate of the forward is equal to the rate of the reverse. So that goes back to this particular diagram. Now, but when I increase, in this case, the products, going back to reaction kinetics, remember, when you have an increase in products, what happens is the rate increases. So in this case, if I've increased my product, I've increased the concentration of my products, the number of effective collisions the products are having is more than the number of effective collisions the reactants have. As a result, the products going to reactants would be at a faster rate because of a higher concentration. And so that's why I said it would favor to the left, to the reactants, or to the reverse rate is favored. Now, what would happen in this particular case? The result is that you would have an increased concentration of reactants because the reverse rate is favored. Okay. And you would have a decrease in the concentration of the products. Now, going back to reaction kinetics, you remember if the reactants increase, the products decrease, and vice versa. Now, one thing for you to be aware of is, I'm just going to put this down here, make sure you are aware there is a new rate at equilibrium. Okay, so please be aware there's going to be a new rate. Why? Is because overall you've increased the concentration, and so as a result, the rate changes. Okay, again, it goes back to this idea of concentration and rate. Again, if you were in my class, what would happen is I would explain in a little bit more detail why. But if not, if you weren't in my class, I'll try to put a video in the description box below. But if not, do come in and see me, and I can explain this particular concept in detail. All right. Now, what is another change or another stress that we could apply to an equilibrium. What we could have is we could have a change in pressure for gases only due to volume changes. Okay, now for grade 12, we are just focusing on the changing of the volume. For if you are an AP, I will talk about change in pressure due to an increase of non-reactive gas in a second. So an increase in pressure due to a change in volume, what will happen is that will shift the equilibrium in the direction of fewer molecules. Okay, you could think of it is that you have a lower entropy. So if you increase the pressure due to a change in volume, the equilibrium will shift in the direction of fewer molecules or favor the side with lower entropy. Now, one thing for you to be aware of is this. Notice the inverse relationship between pressure and volume. So when you increase the pressure, the volume is less. Makes sense. If you were to crumple, let's say you had a favorite stuffed animal and you were to squeeze the stuffed animal, what happens is you have a lower volume. Your stuffed animal would be a lot tinier. If you released your stuffed animal, what would have is you would have a bigger volume. So there's an inverse relationship between pressure and volume. Now, this idea of increasing pressure or decrease in volume with a lower entropy will occur only if you have an unequal number of moles of gases on either side of the equilibrium. Okay. Now, let me give you an example here of what do I mean by this. Okay. So I'm just going to focus on this part here. So, whoopsie. So let's say, for example, come on. There we go. Come on. Yeah. There we go. All right. So let's say, for example, I have 2H2 plus 1O2 gas would be in equilibrium with 2H2O gas. Now, if you take a look on the left-hand side, in this case, what you have is you have 3 moles of gas. Here, what you have is 2 moles of gas. Where did I get the 3 and the 2 from? So here would be 2 plus 1 would give you the 3 moles. What? And here I have the 2 gives you the 2 moles of gas. Now, again, just like before, if I were to talk about the stress, shift, and the result, here, if I were to talk about the stress, here, if I increase the volume or decrease the pressure, what would happen is the shift is you would have a shift to the left or to the reactants. Now, why would you get a shift to the left or to the reactants? Is because if you are increasing the volume, what happens is that you have more space. And since you have more space, it would favor the side with greater entropy. Remember from last day's lesson, all chemical reactions tend towards the side of greater entropy or greater randomness. So if you have more space, hey, it allows for more randomness. Okay. Now, an example would be like, way you could think of it is this. The bigger the amount of space in your house, the more stuff you can have. You have more randomness. Now, let's say you had a big house and you were downsizing. What happens is you would have less stuff because you're trying to get rid of the materials. Same idea here. In this particular example, because I have more volume, you are able to have more molecules so that you have more randomness. If you decrease the volume, what happens is you have less space, so you can only have less number of particles, so you have less randomness. Okay, so please be aware of this idea, all right, about how volume and randomness are related. Now, the other thing for you to be aware of and note again, what is the relationship between volume and pressure, that inverse relationship? Now, if I were to take a look at my result, since it was shift to the left, the concentration of the reactants would increase and the concentration of products would decrease. Again, why does it increase or decrease? Why is it opposite? Goes back to reaction kinetics. As one goes up, the other side goes down. Okay, so just something for you to be aware of. Now, the last one, or sorry, number 3, is a change in temperature. This is the one that sort of gets people a little bit confused. So when you have an increase in temperature, it will favor the rate of the endothermic reaction. Now, in this particular example only, okay, you notice here, energy is found on the right-hand side. Okay, this is found in the products. So what happens is this. In the forward direction, if I'm going from left to right, this would be considered an exothermic reaction. If I were to go in the opposite direction, in the reverse, going in this direction, this would be endothermic. Now, so one thing you have to consider is that when you look at a chemical reaction, there is an exothermic reaction and there's also an endothermic reaction. So you might say, well, Mr. Chan, which is which, right? In this particular scenario, what happens is if I don't state it, we always, by convention, we always think that this is the reactants going to here would be the products. So by convention, we always say that the reactants are on the left, the products are on the right. We read it from left to right, unless I specifically state that I'm going in the opposite direction. So in this case, if we look from left to right, what happens is the energy is in the products. So in this particular case, if the temperature increases, the equilibrium will shift towards the reactants increasing the concentration of H2 and I2, decreasing HI. Again, for this particular reaction only. Okay. Now, why does that occur? Is because the reaction is initially at a constant temperature. And when the temperature is increased, the reaction will want to suck in the extra heat. So for the reaction above, the reaction will move towards the reactants. Again, for this reaction only. And the reason why this is only for this reaction is because the energy term is in the products. All right. Here's the way that I explained it in class. You could think of it like this. So let's say we have our original equilibrium temperature. So what happens is, I'll use a red. So in this case, if we increase the temperature, this is my stress. Is I've increased the temperature. Okay. So what happens is that we have a new temperature. Now, the issue with this new temperature, now it is too hot. So what we would want to do is we want to bring that temperature down. And to bring the temperature down, what would happen is what we would need to do is we need to cool the reaction. So to cool the reaction, that is an endothermic reaction. Or what you could think of, instead of cooling the reaction, we need to lower the temperature. That would probably be a better way. So remember back from grade 11, grade 10, whenever you lower the temperature, what that is the endothermic reaction. So in this case, this would be considered my shift. And so what happens is, in this particular case, the result is, I'm going to say, you could think of it, you want the original temperature. So what happens is, when you increase the temperature, that's your stress. The temperature is too hot for the reaction, so the reaction wants to absorb extra energy to bring that temperature down. And so what happens is, you have what's lowering the temperature. What type of reaction lowers the temperature? It would be an endothermic reaction. Now, so that's why we have it. When the temperature increases, it will favor the reactants because you need to lower that temperature, which is the endothermic reaction. Now, a way you could think of it is like this. Let's say in your household. Originally, in your household, you're at a nice temperature. Okay, so that's where we have the original temperature here. Now, let's say in the summertime, that's the stress. The temperature gets too hot. Okay, so the new temperature, the temperature gets increased. It's too hot. It's too hot in your household. What do? You need to cool down. Some of you turn on the air conditioner. Some of you go to Metrotown to cool off. That is like Le Chatelier's principle. If the temperature gets too hot, it wants to cool down. And so by cooling it down, how does it cool down? It favors the endothermic reaction because it absorbs the heat. And so just like you turn on the air conditioner, it brings the temperature down so that it's comfortable. Now, conversely, if we were to use this rationale, let's say in this particular case, my stress here is I decrease the temperature. And what you have is the new temperature is the new temp is too low. So because the new temperature is too low, what you want to do is you want to increase the temperature. So you want to increase the temperature. This is like the exothermic reaction. Again, and this is my shift. All right, to bring the temperature back up to the original temperature to the best of its ability. All right, so when you increase the temperature, that is the exothermic reaction, because increasing an exothermic reaction increases or generates heat. So if we were to take the example of your household, let's say in the wintertime, it gets too cold. What happens is that if it gets too cold, I know in some families they tell you to, put on a sweater. But if it's too cold, some of you might say, oh, I need to turn on the furnace. Why do you turn on the furnace? It's because you're generating heat. So an exothermic reaction would be like turning on the furnace because you are generating heat. So you're bringing things to warm up. So that's the idea that you can take a look at, is that when the temperature gets too high or too low, what happens is the reaction either wants to generate heat or reduce the heat to bring it back down to the original temperature to the best of its ability. And how does it generate heat or absorb heat is basically either, in this particular reaction, is either favoring the products or favoring the forward reaction to generate heat because energy is in the products, or to absorb heat, the endothermic reaction, okay, in the reverse direction. All right, so hopefully this one's a little trickier, but hopefully some of you can reconcile what I've shown up here in the top with what this little diagram here on the bottom is showing you. All right. All right, the last one is this. A catalyst has no effect on the equilibrium system, no shift. It only affects how fast the system gets to equilibrium. When we take a look at catalysts, a catalyst speeds up both the forward and reverse rates. The same amount. So this is why there is no shift. Yes, a catalyst speeds up a reaction. It speeds up both the forward and the reverse rate, but because it speeds it up the same amount, what happens is there's no shift because no one rate is greater than the other. All right, my friends, hopefully that has been pretty clear. If you have any questions, again, my suggestion is do come and see me. and I can explain it in a little bit more detail. Hopefully, I was able to find a video and put it in the description box below to explain, especially the concentration one. Okay. I will see if I can find any on temperature and pressure. All right. Thank you very much. Have a great day. Bye-bye.